think about projective spaces. This is the minimal thing I told you. But one could do it much better, but because of lack of time, I will only do what I need it and what I will use it. And probably the other subjects you might have studied projective spaces may be better. All right, so now last thing we have seen was this group PGL operates on PV. PGLV operates on PV. What is PGLV? PGLV is GLV mod center. And as I wrote at the beginning of the last lecture, that these three exact sequences you have to remember it. So the special linear group, general linear group, the multiplicative group of a field, PGL, center of the GLV, PSLV, and so on. And our aim is to prove that PSLV is not is simple a group. PSLV is a simple group. That is what our aim is to prove. And I must say that these groups has a lot of geometry. It contains a lot of geometry. Also, it has a, you might have seen in complex analysis, they have also good connections with complex analysis. They have also very good connection to Galois theory and many other branches. These groups are very important in study. All right, so let me start now. What am I going to do today? Now, you know, PSL is a subgroup of PGL. And this bigger group is operating on the projective space. The smaller group is also operating on the projective space. And we are going to understand this action little bit better. And that is what will prepare us for proving that PSLV is simple. And then later on we will see that when is it isomorphic to alternating group and so on. All right, so let me just start recalling. So what is our notation today? As usual, K is arbitrary field. K is a field, arbitrary. And as you see, we will do it for K is a finite field. That is why the PSLQ is simple. And there is some little exception for n equal to 2, 3. All right, K is a field and V is a K vector space. We will always assume finite dimensional and I will put n equal to dimension V. And then we have defined this group P, G, L, V. So if you want to do in terms of the coordinate, then it is P, G, L, and K. Exactly the difference between V, the vector space of dimension n, one could take it K power n by choosing a basis and giving an isomorphism. V is isomorphic to this, and therefore, if you choose a basis, this choosing a basis is giving this isomorphism, and that means coordinates. But I want to do as much as possible coordinate free. So these groups are same, they are isomorphic because of these vector spaces are isomorphic. And then there is a projective space here, PV. Similarly for this, it is P corresponding to this is Pn minus 1 K. This is an n minus 1 dimensional projective space. Projective space. And the points in the projective space are precisely the lines in V passing through origin. And then we saw how does this group operate on this. No? All right. Now PSLV is a subgroup of this that we saw. So this will correspond to the special linear automorphisms, and these are general automorphisms. They are arbitrary automorphisms. Special linear means their determinant is 1. So when I write F is ought V or same as GLV, that means F is an automorphism. Automorphism. And this group PGL is a quotient of this group by going modulo the center. If you ever forget, keep this, remember. See, PGL is GLV mod the center. And then PSSO, what is the operation? So how do this group PGLV operates on PV? I'm recalling that. So that means we should have this map, operation map, PGLV cross PV to PV. This should be our operation map of this group. Very simple. Take any projective linear transformation, that is we are denoted by like this. You remember? Corresponding to this F. And take a point in V. So that point will look like X. This is a notation for the vector space, subspace, and one-dimensional subspace generated by that X. So X has to be non-zero. And this one should go to another point. And then we have defined this F operating on this X. And what was the definition? The definition was precisely you first operate F to X and then take the corresponding point in the projective space. That was the definition. Note that X is non-zero and F is an automorphism, therefore Fx is also non-zero. So therefore this is indeed a line in the V, and which is also passing through 0 because F of 0 is 0. All this is built in very nicely. So this is a very natural operation of PGLV on PV. So this is a canonical operation. And such kind of operations happens in every field of mathematics. Groups, rings, and field extensions everywhere. All right. Now I restrict this operation to PSLV. So PSLV cross PV. This is a restriction of this operation. So what is the extra thing we have? We have this F here. And F is not arbitrary, but the determinant of F is 1. And comma point in projective space X. How does it operate? Again the same. I will just now directly write Fx. This is another point in the projective space. So this is also a canonical operation. All right. Anybody has a question, please don't hesitate to ask. In fact, I would be happy that if you are asking questions, and unhappy that you are not talking. All right. The first observation I want to make is this group, this action of PSLV on PV is doubly transitive. Not just transitive, but doubly transitive. So first I will recall what is doubly transitive. So it's very simple. When do you say group operate doubly transitive, let us recall more generally. So recall that so suppose X be a G space, that that means X is a set and G is a group and G is operating on X. We have seen when it is transitive. G operates transitively on X means that is X is non-empty and only one orbit. One G orbit, namely X. That means what? That means given any two elements X and Y in X, there exists G in G with Y equal to Gx. That means Y and X are in the same orbit. I am not saying G is unique. If G is also unique, then you call it a simple transitive action. So that was a transitive. And now it's nothing special about one element. I want to define, now I want to say that G operates doubly transitive or some people will also write two transitive. If it is more than transitive, what more? Given any pair X and X prime in X and Y prime in X, there exists G in G such that Gx equal to Y and Gx prime equal to Y prime. Then you call it doubly transitive. And this is for any pair XX prime and any pair YY prime, you should be able to find one G which will map X to Y and G prime to Y prime. In particular, it will be transitive. I can take X equal to X prime, Y equal to Y prime. All right. Now I want to prove it to you that this canonical action of PSLV on PV is doubly transitive.
Sir, in double transitive, you mean some equality does not happen, right?
Which equality?
I mean, if X equal to X prime and Y not equal to Y prime, then we cannot have any G which.
I don't understand. Is it a question or are you answering? Are you telling me something?
It's a question actually. X can be equal to X prime.
Can be equal to, but may not be equal to.
But in that case, if Y and Y prime are distinct, we cannot find any G, right?
Why?
Then X will be going to.
I never said any condition on X and X prime and Y prime.
So, but G of X can take only one value.
Fine. Then in that, if Y is different from Y prime, then the X prime is also different.
Yes.
All that what I'm saying that doubly transitive implies transitive because I can take in this definition X equal to X prime and Y equal to Y prime.
Okay, sir.
All right. All right. Now
Yes, sir.
I want to prove now a proposition. The canonical operation of PSLV on PV is doubly transitive. Proof. So I take 2 points, X and I want to keep it the same notation, X prime in PV and also Y and Y prime in PV, and I will take them different. They are not equal points. They are not equal points. Then what am I looking for? I am looking for an element in PSLV. So I will write down what we are looking for. We are looking for F in PSLV such that F evaluated on X is Y and F evaluated on X prime is Y prime. This is what we are looking for. Looking for F. What is that F coming from? It should be a linear map and it should be special linear map. So in other words, so what are we looking? Again, rewrite it. That is F in SLV such that this equality means what? This I know it is F evaluated at X and then taking that subspace generated by that Fx. So such that Fx and Y, they generate the same subspace. And similarly, F of X prime and Y prime, they generate the same subspace. That means they are the same lines. I have not done anything, I have just translated. Any proof, any example, you have to do it like this. There is no other way to do mathematics. First, try to understand what is to be proved, and then try to prove it. And keep asking yourself what is given, what is given, what is to be proved. That is how it should go on. And even if you get stuck, you get ideas. Specialize in that case, then you get ideas. All right. So this is what I want to do. And what are X and X, Y, X prime, Y prime? They are elements in the vector space and they are all non-zero elements. X, X prime, Y, Y prime, they are elements in V and all are non-zero. And then you are looking for F. That means you are looking for a linear map. And you know how do you produce a linear map from V to V? You define on a basis. Choose the appropriate basis and define on that. That is how you have lot of flow of linear maps. You have a lot of freedom if you have a basis. So you have to choose a basis. All right. So what am I going to do? I have these X and X prime and Y prime. And they are different points. What do you mean? What does one mean by different points? X not equal to X prime means what? That means Kx is not equal to Ky X prime. See here, that is also given to us. So Kx is not equal to Kx prime. What does this condition means? This condition precisely means x and x prime are linearly independent. And think geometrically. You see here, this is a line. This is one line. And this is another line. So, therefore, they are passing through origin. So this is x prime and this is x. And you see these vectors, they are not linearly dependent because they are not on the same line. That they are linearly independent. Similarly, y and y prime, that is also given they are not equal. So therefore, we also know that ky not equal to ky prime. So that means y and y prime are linearly independent. Over k alone, of course. Now I will write here x prime. These are two linearly independent vectors in V. I will complete it to a basis. I know if I have given any subset which is linearly independent in V, I can always extend to a basis. So I will call this as x1, this as x2, and complete it to a basis x3, xn. This is the basis of V. Similarly for y and y prime. So y prime are linearly independent. So I will complete it to a basis. So this is y1, this is y2, y3, yn. This is the basis of V. Any two bases of the vector space have the same number of elements. I have this. I have a basis. Now I want to define f. And what is my requirement? Then obviously, what am I going to do? I will map x to x1 to y1, x2 to y2, x3 to y3, xn to yn. So I will get my map f. But now, this is an automorphism is fine because basis is mapped onto basis. But I have to also make sure that the determinant is 1. Now, whatever map I have got defined, that will have some determinant. And I want to modify this map. What will I modify? So suppose let us call this map as G. And then let us call determinant of G det determinant of G equal to some constant A. This is A in K, and it is because it's an automorphism, this has to be non-zero constant. And now I will modify the G by putting somewhere A. Not A, but A inverse. So if I now modify this map, easiest modification is I do it here. A inverse. Now what will be the determinant of the new map? This A inverse will come out when you compute the determinant. And therefore, the new F will have determinant F equal to A inverse times determinant G, which is A inverse times A, which is 1. So I got a linear map whose determinant is 1. And also, actually, I can make this A inverse anywhere I like it. But I will not make it if n were at least 3, then I could have made it here. Right? Why do I do that? Because then obviously I don't even have to bother to check. It's correct, but I don't even have to bother to check that x prime is going to y prime, this line. Because this just a vector is scaled. So the lines will not change. And therefore we proved that the action is doubly transitive. Now I'll give 1 minute gap and wait for your difficulties to ask. If you don't have difficulty, I'll continue. Sonakshi there? Hello, Sonakshi.
So Sonakshi is not there. She is not feeling well.
I can't hear you very clearly, Roshni.
Yes, sir. She is not well today.
Okay, fine.
Sir,
Yes, please.
in the above, I just did not understand the last part, that how did we make that linear map to belong to special linear group?
Special linear.
Yes.
You have
Is it?
understood my definition. You have understood the definition of G.
Yes, yes, sir. Everything. This is the last thing. That dit of G is A.
So I just modify G. So look at the determinant of G. It is a non-zero constant that we know.
Yes, sir.
So if it is 1, we are happy. I don't need any modification.
Yes, sir.
If not 1, then I look at A inverse. Right? A inverse is again, yes.
The A inverse is multiplied to any of the vector in the image.
Yes.
Okay, fine.
Yes. Any vector will do it. Any place you want to put A inverse, whether it is in y1 or y2 or y3 and so on, it will do it. So simple. All right. So if nobody has difficulty, I will continue. Rahul. Hello,
Yes,
Rahul.
sir.
Do
Yes,
you have
sir.
any? Is it clear?
Yes, sir. It is clear to me.
All right. What about Ramveer? Ramveer?
Yes, sir. It is clear to me.
It is clear. Very good. Now, okay, now let me start. What my proof, the way I will arrange my proof of the simplicity of this PSL V. Some part will be put in the exercises, some steps. Small steps I will divide, and some small steps I will put in the exercises, and we will tie up here. That is the idea. Otherwise, it will take long time. So remember, I want to prove this following theorem. So I will already start a proof. So theorem, what we are proving is the following. The theorem we are proving is PSLV, PSLFP, PSL. So Q power of prime power of a prime number P and FQ we are denoting a field with Q elements. That exists we know. So I will just write here exist. That you should make sure that you know this. And then I want to prove that P, S, L, N, F, Q is simple. Okay, before I prove, I should tell you some history, how it went on. As I already said, the starting point was Jordan. Jordan proved this in 1870. for FP. That is where he has to prove Jordan canonical form. And he was the one who started all these characteristic polynomial, minimal polynomial, and analysis with the linear maps. All right, now the next improvement was done by 1887. This was by Dixon. And Dixon proved it for all finite fields. But okay, so that was it. And then comes 1901. This was Moore. He again proved it for m equal to 2, n equal to 2. And he was the one who said the exceptions. What are the exceptions? If you look at the pair n comma k, k is a finite field. So I will write this. N comma fq. This should not be one of the two. 2 z mod 2 or not equal to 2 z mod 2. Understood the exception? For these cases, the group is not simple. That we will see after we tied up the things together. And the proof I am going to give, that is due to Iwasawa. Which came in 1941. See, the earlier proofs are matrix in terms of the matrices, and one doesn't see so clearly the geometry there. But the Iwasawa proofs contain these group actions, and therefore one can look at it more geometrically. And that is perfectly fits in our course here because we have done group actions very well. That is that. Okay, now let us start proving it. So proof, and proof I will write the steps. Proof. So what is that we want to prove? We want to prove that there is no non-trivial normal sum. So the first step I will prove. First step already we have proved. This is the first step. That the operation is simple, doubly transitive. Okay, so I will write this as a first step. So this is the first step. So start with a normal subgroup. N non-trivial. And let me write now the group G. G is fixed, that is PSLV. PSLV and V, dimension of V over FQ is N. This is a finite dimensional, n-dimensional vector space over a finite field FQ. Or sometimes when I want to write matrices, matrix form, sometimes I will write this group also as P, S, L, N, FQ. But the meaning is understood. They are, when I talk about PSLV, I will say the linear maps, special linear maps, and what the center. Otherwise, the matrices, n cross n matrices over FQ, special, that is determinant 1, and modulo the center. So that is So G is our group, that G, and we want to prove that G is simple. That means we should not have a non-trivial normal subgroup. So start with a normal subgroup, which is not trivial and not the whole group G. Normal subgroup, normal in G. And what do I want to get? I want to get a contradiction. Either I want to get a contradiction or I have to prove n cannot be equal to G. So let me keep that open because I don't know, I don't want to tell you what we will lead to somewhere. So this is a normal subgroup. Then to prove, so right here, we are hoping to prove that n must be equal to G. That is what we want. All right, now we know that this group is operating doubly transitively on the projective space, PV. And now allow me to write, so this Pn, PV, I will write the points capital P, capital Q and so on. And what is capital P will mean? It will mean a line passing through origin in V. Q, instead of writing like this, instead of writing P equal to AX or writing, we remember we are writing like this, I will write P and Q. That is understood. P and Q are points in the projective space P. That clear? Because otherwise our notation will become complicated. We don't know what will happen and so on. All right. So we want to prove this, and this step will come at the end. I'm in the first step only. I'm making some observation. So assuming n is not equal to G, I want to make some observation. Because ultimately we want to prove n equal to G, and then I will contradict this cannot be satisfied, therefore n has to be equal to G. That will be the argument. So what is the observation I am making? I am making the observation that n, now G operates on PV that we saw, and the operation of G on PV is doubly transitive. And I have taken n a proper normal subgroup. Then I say that n operates restriction on PV transitively. We know bigger group is operating doubly transitive. But if there is a normal subgroup which is proper, then that n has to operate on PV transitively. What does that mean? That means given any 2 points, so that is given any 2 points P and Q in PV, P not equal to Q, there should exist an element A in N. Oh, let me not use A. What can I use? I don't want to use A, then you will get confused with the scale. Given any element G in N such that G P equal to Q. That is the transitive action. Any P and Q, I have G which carries P to Q. That is what I want to prove. And let me again choose the this. I want to keep that G free, so I will not choose G. But what can I choose? Let me choose H. Understood? This is what we are looking for. Now, we are assuming, I am assuming n is at least 3. Why am I assuming that? Look here. These are the exceptional cases. N equal to 2 is a bothersome case. So I will, right now, I will not bother about n equal to 2. We will tie up later at the end when there is a, so we are assuming now n is at least 3. Not n, sorry. The not n, this field. So Q is all right. So okay, even if you include this case, I want to estimate the cardinality of PV. So what can you say about the cardinality of PV? What can you say about affine V, cardinality V? What do you know about cardinality V? Cardinality V is equal to n is a dimension, Q is a, so it is Q power n. Right? And Q is at least 2. So I want to assume, therefore, what can you say about this? 2 power n, and n is at least 2. N is at least 2. So therefore, this cardinality, all that I need is cardinality of PV is at least 3. You know the cardinality of PV, there is the V has cardinality so much, so cardinality PV, you know, there are the lines in V. So that is at least 3. That is what I am assuming. That follows from our assumptions. Q is power of P. If P is bigger equal to 3, it's obvious. So PV has at least 3 points. Now, what do I want to use that? Where do I want to use that? See, I have already 2 points I have given, P is not equal to Q. That is what I want to prove. So I can choose definitely third one more point. So choose P prime, Q prime, the third point in PV, which is different from both these. P not equal to Q definitely. P not equal to Q prime. And actually I will show you. Actually I should have called this here. But anyway, I will do something and then you will see. Definitely I can choose a third point. Q prime. All right, now what do I know? I know that G operates doubly transitively. That is what we have observed. Since G operates on PV doubly transitive, there exists G such that G in G, that is why I didn't want G there. G in G such that G maps P to P and G maps Q to Q prime. I have given the pair P and Q, they are different. I have given the pair P and Q prime, they are different. And so therefore I know that there exists G so that G maps P to P and G will map Q to Q prime. This is by doubly transitive H. This pair is different, this pair is different. So there will exist G so that will map to this and this. Now I simply want to take what happens. I know now that because n is normal, G, H, G inverse, this will belong to n. Because n is normal. In G. And what happens to this at P I want to find out. So what is G, H, G inverse operating on P? You know, it's a group action. So first I will apply G inverse and then apply H and then apply G. So this is nothing but GH, G inverse of P. But P goes to P, so this is P. And H maps P to Q. I want. Right? So therefore this is G of H of P. This is G of Q. If I could find H with this HP equal to Q, this is Q prime. That means my new map will map P to Q prime. And therefore I proved transitivity of n on PV because I started with P not equal to Q prime and I found somebody in n which maps P to Q prime. So if you are confused, what I should write a statement given any point P and Q prime such that P not equal to Q prime, HP equal to Q prime I am looking for. So I simply call that P and then call that H of P equal to Q. Whatever it is. And now I have 3 points P, Q prime and Q and then you read this proof. So G operate doubly transitive. If anybody has a difficulty, please ask me now.
Sir, how we are getting that H of P is Q?
See, that's what I said. I want to prove that H operates transitively, right?
Yes, sir.
What does that mean? Given a point P and Q prime, P equal to not equal to Q prime, I want to find H so that H of P equal to Q prime, right?
Yes, sir.
Now you take any H, take any H in G, H in N. See here.
Sir, but how do we know such a H exists in N which takes P to Q?
H will exist, no, in N. There is N is normal, N is non-trivial, so there is H in N. So I take that H.
Yes, sir.
And I am going to modify that H. Okay. So I will, okay, if you want, I will write like this. So we are looking for this, right? We are looking for H so that H of P equal to Q prime. Now I say choose any. So this also I will erase.
Sir, I got it.
But maybe the others who are shy to
Yeah,
ask.
I
So start
understood
with
it.
this,
Yeah.
and now I say choose any non-trivial H prime in N. not identity, not E. And put H prime of P equal to Q. I can put H is given, so H is operating on, N is operating on PV, so in particular H prime of P makes sense, that I am calling it Q. And now I look at, because G at doubly transitive, there is a G, so that G of P is P prime, G of Q is Q prime, and now I look at this. This is again in H, again in N, because N is normal. And now I calculate that. This P equal to G prime of P is P. So G, not G prime, G inverse of P is P, therefore GP is P, therefore G inverse P is P. And now H prime P, that is by my choice, it is Q, and GQ, and GQ up to Q prime. So we are done. This is my H, required H. Done. Roshni, is it clear? Hello, Roshni.
Yes, sir, it is clear. Yes, sir.
It's clear.
Yes.
If anybody has still doubt, I am willing to explain, but you should raise your query. Should I make doubly sure? Tithi, is it clear to you? Hello,
Yes,
Tithi.
sir. Yes, sir.
Reluctantly yes or happily yes?
No, sir. Yes, it is clear.
Okay. All right. So I don't want to. What about Arnab?
Yes, sir, it is clear.
Okay, fine. So what we have proved that N operates transitively. All right. Now the next step. There will be several steps, and it will go up and down, linear algebra, group theory, linear algebra, group action, like that it will go on for next 1 or 2 lectures. Okay, now the next step, that is second. Take any point in the projective space, Q. Q is a point in the projective space, P. If you are not happy, write this as Y. That means this Y is a non-zero vector in V. But I want to do that when it is absolutely necessary, because unnecessary it creates a problem. The more you write, the more is a problem. The less you write, you can be more concise. All right. And we have fixed this point, Q. And now I will consider group action, isotropy, and orbits. These are the most important things you need to understand. So consider the isotropy at Q. What is that? That is a subgroup G suffix Q. This is by definition all those elements G in G such that GQ is Q. And don't forget, what are the G's? G's are the special linear maps and modulo the center. So the G is not a map, but it's a equivalence class, modulo the center. All right. Now, what do you want to prove? This is a subgroup that we know. Subgroup of G. G is a finite group. Remember, in one of the earlier lecture, we have computed how to compute. I indicated you how to compute the cardinality of the order of G. Cardinality of G. It's a finite group. I have taken isotropy. So this is a finite subgroup. Index of this isotropy is equal to cardinality of the orbit. Now, what is the statement I want to prove about this? I want to claim that GQ is a maximal subgroup. of G. That is, there is no subgroup in between GQ and G. There is no subgroup H of G with GQ contained in properly, which contains properly the isotropy and which is properly contained in G. There is no such subgroup. That is what we want to prove. First of all, can you tell me why GQ is a proper subgroup? Can anybody tell why GQ is a proper subgroup? Yes, please. I'm asking a much simpler question. I'm not asking about any H, but I'm saying why. Did you realize why GQ is a proper subgroup?
So the action
Sir,
is
if all,
double transitive.
Yes, please. Arnab.
sir, because the action is double transitive,
Yes.
like if all the G's send Q to Q, then like for a distinct point,
Yes. There are definitely G's which will map Q to some other point.
yes,
And those G's will not belong to Q. Because GQ means those elements of G which will map Q to Q. And you don't need double transitive, just single transitive is enough. Definitely there are G's which will map Q to some other point, and there is definitely other point. That is why I said cardinality of PV is at least 3, we know.
yes.
Because of that. It's much simpler. All right, now let me indicate why it is a maximal subgroup. So suppose there is a subgroup. So what will I prove? Suppose that there exists subgroup H such that GQ is properly contained in that. And suppose it is also not G, then I should get a contradiction. So, right, looking for contradiction. Which contradiction? What contradiction you are looking for? Contradiction to what? You see, that also you have to think. Otherwise, just say looking for a contradiction. Which contradiction? Which is the contradiction? What is
So
looking for which contradiction? Anybody guess?
So we can show then that H equals to G, that will be a contradiction.
No, I am assuming H is not G, and then I am looking for a contradiction. Then what contradiction we should look for? What are so far we established? We have established two things so far. G acts doubly transitive. So I will show you if such a thing happens, the action of G cannot be doubly transitive, and that is a contradiction. Is it clear? So contradiction to what? Contradiction to the doubly transitive operation of G. G on P. That is the first step we have proved, no? Here, double intransitive. We'll contradict this proposition. All right? All right, we have to hurry it up because I have to finish this step. So now our assumption is isotropy is properly contained in H and H is properly contained in G. Now what can I do? I take the cosets. G is a subgroup, proper subgroups. So I take the cosets of H in G. And they are definitely more than 2. Bigger equal to 2. Index is at least 2. So therefore, let us look at the cosets. AJH, J is in J, and cardinality J is at least 2, and these are distinct cosets. Of H in G. Then I look at Xj subsets. These are the subsets of PV. Which subsets? Take these cosets and evaluate them at Q. So this means these Xj's are AJ. No, why did I call AJ? Let me call GJ. GJ, any H in H, and evaluated Q, and what is varying is H is varying. And these are subsets of PV, and J is varying in J, and we know cardinality is at least 2. So I claim that this Xj, J in J, this is a partition of PV. What does that mean? This means PV is the disjoint union of Xj's. This I will not check today. I will ask you to check this. This is trivial. This is only set theory. There is no groups involved in this. And the next one I will ask you to check and come tomorrow. And what is that? I will write in violet color. Check that for every G in G, G of Xj is some Xi. I in J. So that means if I operate G on these subsets, it go to the another subset. So that means this partition is permuted among themselves. And this is very easy. You take another G and what will you do? These edges are defined in terms of the coset. So you will have to consider, I will write in the bracket, you will have to consider G, G, J, H, this coset. But this is another coset. This has to be another coset. For some I. And then that checking is easy. There we have to use that Q is fixed under GQ, and GQ is contained in H. And note GQ is contained in H. Use this to check this. Now, cardinality of each Xj is at least 2. Because what? This cardinality of, see, this H has index 2. So use that, and then you will get contradiction to So use this fact to conclude that GIH to GJH. And that will contradict to the doubly transitiveness of G. That's all. I will stop today because already 5 minutes are over. So if you have some, think about this. Mostly if you think clearly, then you will get the proof. You still have difficulties. We will either discuss in tutorials or we will discuss in the beginning of the next lecture. I will stop and I will send this file to Purnashri immediately. Purnashri, when do you have the tutorials?
Sir, this week Wednesday and Friday. Friday though, I think so.
Wednesday and Friday. And what are you doing on the tutorials? Which
Sir, this week I asked them to submit the 4th assignment by tomorrow.
okay.
So, depending upon that, I will decide what to do.
Fine. This is lecture 17. All right. So I am sending it to Makaran and you can give it to them.
Okay, sir.
All right. Then see you tomorrow. Please collect your difficulties for asking. Think about it and come back. More. Okay. Bye bye.